Good, thank you very much. So today we're very pleased to have Fred Weissler, who is somebody that I have known. Fred and I have known each other for a very long time. We often meet in Paris rather than here, but both places are very nice. And this is the last talk of our semester. We can be expecting some interesting talks next semester, but we've got a rest for at least a month. So Fred will talk to us on blow-up and local ill-posedness for the complex periodic Korteweg-deVries equation. Thank you, Fred.
Thank you, Susan. And thank you very much for affording me the opportunity to present this work here at USC in the Applied Mathematical Center for Applied Mathematics. And so I'm going to talk about some joint work with Jerry Bona. And if I may say, this is actually work that began about 25 years ago that has evolved sort of like an amoeba until we finally decided to write it up. The parts had been written up before. And so let's go on. So the plan of the talk is not very imaginative. We'll begin with the introduction, talk about finite time blow-up, local ill-posedness, and if there's time, some remarks about some analogous questions for systems. All right, so just brief history. I'm sure most of you are familiar with the fact that the Korteweg-deVries equation has a very rich mathematical history and has led to the study of this equation, has led to many different fields in differential equations. So it was just briefly introduced by Boussinesq in 1877 as a model for shallow waves in shallow water. It was rediscovered by Korteweg and deVries, which is why it's called the Korteweg-deVries equation. And they found the very well-known one soliton solution. And then a little later, there were some important numerical computer simulations. And just at that time, you see there was a lot of activity in the late 60s where the inverse scattering transform and the infinitely many conserved quantities and led to the notion of completely integrable equations. And then Lax reformulated as the Lax equation. I suppose he didn't call it the Lax equation at the time. And then the first local well-posedness. So this is an initial value problem, or can be considered, because time is one of the variables. And so you can think of the equation. You have an initial condition, and you want to function depending on space, which represents the height of the water or something like that. And I'm not a physicist, so I won't go beyond that. But you can then say, well, what kinds of initial configurations lead to reasonable solutions? And so the first result that I'm aware of is the 1975 result of Bona and Smith, proved local well-posedness for S and HS for S bigger than 3/2. And then because of the conservation laws in H2, we're able to get global well-posedness. And then just briefly, you can see some subsequent different methods used. The inverse scattering, Kato used the fixed point argument. As far as I know, that's the first fixed point argument that was used, but there may be other people who know more of the history than I. Then Koenig, Pons, and Vega had a different method to try. The idea was to try to get, this is so H and HS for S bigger than 1/2 rather than S bigger than 3/2. Kato had some exponentially weighted spaces. And then it was, in some sense, the big breakthrough, if you wish, was 1993 by Bourgain, who introduced what are today called the Bourgain spaces, and was able to prove local and global well-posedness in H0. So H0 is L2, and I'll be mostly interested in L2 and maybe H1 in this talk. And then the last paper I'll cite, and there's been a whole slew of papers since, the subject hasn't stopped there. And they proved the game in some sense, or the game that they were playing, and that many people have played, is to try to find the weakest, the largest space in which you have local well-posedness, and to try to see what the limits of that are. And I'm not so much interested in negative Sobolev spaces. I'm interested actually in this paper in the case S equals 0, which is the same thing that Bourgain did, but I'll explain in a few minutes why this paper was so important. So that's just a brief background to sort of set the stage for what I'd like to talk about. So there's the equation again. So U will be considered as a function of t, which represents time, and x in R, but I will be interested specifically in periodic solutions, 2π periodic solutions. And so we will consider them to be as solutions on the circle. And the important thing is, as everyone here knows, that any function on the circle can be represented by its Fourier series in terms of exponentials, the sum from k equal minus infinity to infinity, ak e to the ik x. All right, so the result of Bourgain, 1993, is that the Cauchy problem for KdV is globally well posed, and he did it both on the line, but this talk is going to be focused on the circle in HS of S1 for all integer S, all non-negative integer S. So for an L2, H1, H2, etc. And then the Koenig, Pons-and-Vega paper in 1996 extended that for negative X. In Stafilani, of course, then I didn't talk about the generalized Korteweg-deVries equation where you put in a higher power, and that's, again, not going to be the focus of this talk. So how do you prove global well-posedness? What do you mean? It means that you have, for any initial value, you have a local in time solution, and then you use the conservation laws to prove global well-posedness. So I'm speaking somewhat vaguely here, but now I want to sort of examine the two steps here. So there are two steps. There's the step of local well-posedness. There's the step of the conservation laws, and those are the two steps you need. So what are the basic conservation laws at the level of L2 and H1? So the mass, the average, is a conserved quantity. And as I mentioned, that this equation actually has infinitely many conserved quantities, but I'm just going to be interested in these first few. Then the conservation of charge. So the integral over the circle of U squared is conserved in time. And then there's an energy functional here, which is the, as you see, the integral of the square of the derivative and the integral of U cubed with various coefficients. And that quantity is conserved in time. And then going again, I'm intentionally sloughing off I'm intentionally ignoring a certain point, which I mentioned at the end of the slide. That is, the conservation of charge implies that the L2 norm is constant. So if you have, so what does local well-posedness mean in L2? It means if you have an initial value in L2, you have a local and time solution. And you know that if you want to prove that it becomes global, one way to do it is to show that the L2 norm stays bounded. And of course, if it's constant, then it stays bounded, and then you have a global solution. Then if you're interested in H1 solutions, you can play the same game in the sense that the conservation of the energy, the conservation of the charge, along with Sobolev inequalities, allows you to get a priori bound on the H1 norm. So if you have local well-posedness, then you also have global well-posedness. But the point that I'm ignoring here, which I mentioned at the bottom, is that the conservation of charge, is the square of U. It's not the square of the modulus of U or the absolute value of U. So but the thing is, so here's sort of the point that's sort of overlooked in a lot of the papers. The original equation was a module of order waves. So it was sort of assumed without even stating it that these were real valued solutions. And so if you look actually at Bourgain's paper, and if you look at Stafilani's paper and several other papers, they never say whether they're talking about real or complex valued solutions. And this is especially frustrating because the methods you use to prove local solutions are Fourier analysis, which work perfectly well for complex valued solutions. And so this point is sort of never sort of explained in the papers, except for the Koenig, Pons-and-Vega paper. So I will come to that. So the first thing that I want to emphasize is that these conservation laws only give the kinds of bounds that enable you to prove that a solution is global in the case of real value solutions, and this talk will be about solutions that are not necessarily real value. So that calls this into question. Now, what about local well-posedness? Because here there's another point which is worth explaining. So how do you prove local well-posedness? Well, this is extremely complicated with all the different techniques that were given. But if you look at the Bourgain and the Stafilani papers, what they do on the circle, and also the Korteweg-deVries paper, is you reduce it, you consider first initial values on the circle with mean value 0. And you develop your entire machinery for local existence, local well-posedness, for solutions which have mean value 0. And these work, first of all, the mean value 0 is preserved by the conservation law, so it's certainly reasonable to look at that subspace, the subspace of L2 or H1, where the mean value is 0. That just means that the constant Fourier term is 0. In other words, the Fourier series, you just don't have the constant term, it's just e to the ikx for k different from 0. And it uses, again, the Bourgain spaces, and this applies to complex valued solutions. Now, how do you then go from complex valued solutions with mean value 0 to solutions without mean values 0? Well, it turns out there's a very simple transformation. So if you have a solution on the circle U with mean value 0, and you define U tilde this way, or inversely, I mean, you can write the inverse transformation, U tilde is now a solution of KdV with mean value A over 2. The problem is because the A is right there and U is a function of x minus AT, this formula doesn't seem to make any sense if A is not real. And this point is, so the Korteweg-deVries paper, the 1996, they were the only paper, maybe this is going to be recorded. If this is being recorded, well then, well, I'll just continue saying this. Yeah, I don't write this down, but they actually say, all right, they prove it, and they state very clearly that their local existence is for complex value solutions. But then they say you extend it to solutions other than mean value by the standard trick, and this is the standard trick. All right, so, but this trick requires A being real. So what are the unresolved matters? The first unresolved matters are the local existence or not of a solution in the case of an initial value with complex non-real mass or mean value. All right, and the second unresolved matter is the global existence or not, I mean, finite time law, of a solution in the complex case with non-real solutions, whether or not they exist for all time. So why would one be interested in these two questions? Well, the first admittedly is you could say is a technical point, but it's nonetheless, at least to my way of thinking, an interesting technical point, because if you're now going to be studying well-posedness in negative Sobolev spaces, you don't want to leave this unresolved. The second question of glow-up has a very specific reason, and this was the reason that Jerry Bowen and I began studying this. We have a number of papers on complex valued solutions, not on the circle. And then going back to the higher order equation called the generalized Korteweg-deVries equation. For real value solution, it's known that if k equals 2, which is Korteweg-deVries, 3, which is the modified Korteweg-deVries, or 4, all solutions are global by those conservation laws for real value solutions. For 4, this is a very well-known result of Franck-Merle and Yves Martel, prove that in the case of k equal 5, which is the pseudo-conformal case, or somewhat like the pseudo-conformal case for the nonlinear Schrodinger equation, you do have solutions that, real value solutions that blow up in finite time. For k larger, it's still unresolved as far as I'm aware, whether or not even real value solutions, the energy arguments no longer work, exist for all time. So the idea that Jerry Bowen and I had were to look at complex value solutions of the lower order equations to see if you have finite time blow up. And if you do, maybe studying that phenomenon will give some insight into here. Of course, we've not yet been able to carry out the second idea, but we have become interested in the question of a finite time blow up for a complex value solution of Korteweg-deVries. And ultimately, it's up to other people to decide whether this is of interest or not, depending on the results that one obtains. All right, so now to get into our approach. So it turns out, so let me write this down here, this subspace, because I'll use this. We look at what I'll call HS0 plus, maybe not the best notation. So what is it? It's the set of all U where the U of X, so I'll write it somewhat informally, sum from K equals 1 to infinity of AK e to the I KX. In fact, perhaps, well, I'll just do it here. So the point is, actually, in some ways, I should have written it on the other side, but if I stand here, is that okay? All right, so the idea is that we look at functions on L2 or HS. So the 0 is because there's no 0 term, that means value 0. The plus because we're only looking at functions that have positive Fourier modes. So in other words, we're only looking, instead of having the full Fourier development, we're looking at functions whose Fourier development only includes e to the I kx for positive k. Now, why do that? Well, one thing is you can see that this set is invariant under KdV. In other words, forgetting time for the moment, if you take a spatial derivative of such a function, all you're doing is bringing it down to k. And if you multiply, take u squared, you have this infinite series starting at a1 e to the ix plus higher order terms times itself. And when you multiply together, the lowest term you have is e to the I2ix. So you do not introduce any modes. And so if you have an initial value of this form in this space, HS0 plus of S1, then at least formally, the resulting solution has to still be of that form. And then if you differentiate that respect to time, in other words, if you take a formula of this type, you can just plug that into Korteweg-deVries, and it's sort of whole within itself. In other words, that there's nothing in the equation that forces you out of the positive modes. And in fact, when you do this and you just plug it in, I mean, it's just, what you get is a series of ODEs for each mode. So you plug in, and then you collect the terms in the resulting Fourier series. You need the A prime of t minus, so I k cubed is the third derivative, it's the uxx term. And the I k b k is the, maybe I should have actually written down Korteweg-deVries. I should mention that other people put different constants here, but that doesn't really matter. And you can just plug this in and collect the Fourier modes, and you get this, where the bk's are the coefficient of u squared. And then, of course, you need the factor of k because you're taking the derivative of u squared. And what you notice, in addition, so as I explained, when you multiply, take u squared, the lowest term is e to the I 2x. So when you take u squared, there's not even a term corresponding to k equals 1. So in fact, each bk, when you take the development of u squared, the coefficient of the e to the I kx term depends only on the coefficients am for m less than k. Because there's no 0 term here. If you're looking for the coefficient, if you square this and you're looking for the coefficient of e to the 9x, e to the I 9x, it only has 1 through 8 in it. Okay, so that means that the bk's are determined iteratively by the previous equation. The one equation is just a linear equation because the b isn't even there. And so in principle, you can write down the complete solution to this system because it's not a system of nonlinear equations. It's a system of non-homogeneous linear equations, which you can write in integral form this way. And in principle, you can just solve them if you have enough time, or if you see a general formula, which we have not. But you can still say, even if you don't see a general formula, which may very well exist, there's a lot you can say and can tell you about solutions of this form. So that's one reason for choosing this particular subspace, because it allows you to say a great deal about solutions in that subspace. And this is not to be surprised. Anytime you have an equation and you have an invariance, using that invariance enables you to simplify the kinds of solutions you have, and anytime you have an invariance, and if you use that in an effective way, it can help you learn about the equation and about solutions that satisfy that invariance, or that have certain properties with regard to that invariance. All right, so what you have here, so I've said a lot of that already. You solve it for iteration, but one thing you can solve, one thing you can say, is that these coefficients exist for all time. In fact, it doesn't depend on any space you're in. This is just a relationship among, let me just go back one slide here. Once you write down that Fourier series, you don't even ask a question. You just say the initial value is sum from k equal 1 to infinity, ak of 0 e to the ikx, and you just put down any ak of 0 you want without even saying, here I said, suppose the initial value is in HS. Okay, fine. You can do that or not. But you can always get solutions ak of t that exist for all time. And you always have a solution for all time. You can always write down that Fourier series, ak of t. Now, what you do not know is that even if you start out at t equals 0 with a function L2 or H1, you do not know, and in fact, it will not always be the case, that the solution stays in L2. But you have what we call a formal solution. So we want to distinguish between an L2 or a classical solution or a HS solution, whatever you want, and what we can call a formal solution, which is just the solution of these coefficient equations. And those exist for all time, backwards and forwards. So you actually then have something to study. All right, let's see, is there something else? Okay, let's see what's the next. Okay, so let me just make a remark on the convergence. So we're interested in whether or not something like this might converge. It turns out to be a useful tool to replace the e to the ikx by z, e to the ix by z, and to consider a power series that you get. And in fact, functions of this type are boundary values of analytic functions on the circle. Because if you have an analytic function and the disk, excuse me, you have an analytic function on the disk, then you put in z equal I to ix, which is on the circle, and you get the Fourier series. So in some sense, what I'm looking at is a very special class of functions which have Fourier series of this type, because they are, at least formally, boundary values of analytic functions in the disk. But now, again, we're not talking about convergence, but we look at that as a power series. You can say, what is its radius of convergence? If the radius of convergence is bigger than 1, that means e to the ix is inside the disk of convergence, and everything is smooth and regular and C infinity and things like that, and you're certainly in L2. On the other hand, if the radius of convergence is less than 1, then you're outside the radius of convergence, and you can't even be in any HS space, because if you were in an HS space, you'd have even a negative space, you'd have some estimate on the coefficients. And then inside you would still have analyticity, because the z to the k, once you're inside, once you have any kind of estimate on the coefficients like HS, I mean, if you're in H negative a million, it doesn't grow any faster than s to the millionth power. But then you hit that with an exponential and it then converges much better. So if the radius of convergence is less than 1 at a given value of t, you don't even have a distribution, because actually on the circle, the distribution are just the union of all those envelope spaces, unlike the line, because there's no decay at infinity. So if the radius of convergence is bigger than 1, you have an analytic, you have a very smooth solution. If the radius of convergence is less than 1, then you don't even have a distribution. Okay, so that means that looking at the radius of convergence of this power series is a useful tool in understanding the convergence of that Fourier series. So let me just give a basic local existence theorem. I won't go into too much detail because we know that the problem is locally well posed in HS, but having this structure allows us to say something else, that if you take an initial value and you suppose that the initial coefficients have a decay, so lambda will be a factor less than 1, so lambda decay is going to be decreasing exponential, and we put in an extra polynomial decay factor, which turns out to be essential. We need sigma bigger than 1 in order to make the estimate go through. We can plug this into to the integral equation, and we can see, so we know the AK of t exists. We know they exist, but if the AK of 0 have this estimate, then the AK of t have a similar estimate for all time. And if you start out with something that decays exponentially, as long as that factor is less than 1, then you still have an exponentially decaying solution. In other words, the radius of convergence is still bigger than 1. And so what you do is you get a minimum estimate for the local existence time in both directions, because you have an explicit estimate on the growth of those AK of t's. Now, what's interesting, and you plug that in, I mean, that requires a little bit of a calculation. And there's a constant L that comes in, and I'm sort of embarrassed to point it out, but I can't not point it out. There's the constant L, and if it's 2 to the power, 1 plus sigma, and you need the convergence of this infinite series. And we're very embarrassed, but that's the Riemann zeta function. And we have no idea why the Riemann zeta function shows up here, but it does. And we don't use anything about the Riemann zeta function other than the fact that that series converges for sigma bigger than 1. But all right, so that's the basic, and we use this local existence theorem to give to have specific estimates on solutions that do exist up to a certain time. So you'll see when we get to the, yes?
Those are analytic, right? Not algebraic. Those are analytic functions, right?
Yes, yes, yes. Once you're inside, everything here is, inside the radius of convergence, everything is analytic.
Because it says Gevrey on top.
Yes, we'll use it because I think Gevrey classes are in fact analytic functions. I mean, they're classes of analytic functions of this type. So we say Gevrey type, We say Gevrey type because I think that the Gevrey spaces are more on the line.
It's like e to the I k to a different, it's e to the k to a different power. If it's power 1, it's analytic. If it's k to a different power.
Okay, yes, okay, but
my advisor.
Okay, so maybe that's, but in any case, we're not claiming they're Gevrey, it's just every Gevrey type, because we know that, but in any case, the key thing is the specific estimate. And of course, these are analytic functions. Once you're inside the radius of convergence, everything is analytic. Okay, so what is our first? So we have 2 finite time blow-up results. Okay, suppose we start with an initial value. Let's just say L2 doesn't, well, the proof will show L2, but it can work for anything higher. So suppose you have an initial value in L2 of that form. And suppose that the first coefficient, the coefficient of e to the ix, is in modulus bigger than 6. Then the solution blows up in finite time. And that 6 is best possible in the sense that you can find initial values with A1 of 0 arbitrarily close to and less than 6, which in fact give rise to global solutions. That doesn't mean it's the best possible in every possible case. And I'll explain that on the next slide or two. But we also want to point out that the first finite time blow-up result for periodic solutions of KdV is due to Werner in 1986 and 1987, who constructed them. So we're not the first people to look at complex valued solutions of the Korteweg-deVries equation. In fact, some of the calculations, there's a paper by Kruskal that, based on some numerical calculations, made some interesting conjectures about complex value solutions. But in any case, Werner was able to construct an explicit blowing up solution based on the doubly periodic Weierstrass's elliptic functions. So it has a more or less explicit formula, which will not be what we have. His formula is not in this space. That one can check. But so how does the proof go? So as I had pointed out earlier, I said, and it's true, you can, in principle, solve these AK explicitly. So what happens if you start working them out? So you want to find the variance. You calculate A1, you calculate A2, you calculate A3, you calculate A4, and the first thing you notice is that they're all time periodic. And that you can prove by induction. So that in fact, these AK of T are time periodic. Let me put that formula here on the board. So I'll probably use this a lot. U of T x equals sum from K equals 1 to infinity, AK of T, e to the I K x. These AK of T are themselves time periodic, 2 pi. And so what you really have then is a double Fourier series. And then you write, I didn't do it on the slides, but then you can write AK of T is the sum of e to the I h t from h equals et cetera, and you have a double Fourier series with coefficients alpha kh. You can plug that into your equation too, just like we've done that. And what you get is now an algebraic relationship between, so I didn't do that on the slides, but what you roughly have is that this will be the sum of various sum of alpha k h e to the I k x e to the I h t. And the alpha kh satisfy an algebraic relationship, which in principle you can solve explicitly. And actually, I spent a certain amount of time looking for a general formula, but did not. But you can find general formula in specific cases. And you can calculate enough of them. So you can look then, since we know it's so how does blow up work? The standard proof is, at least in a hidden fashion, is by contradiction. You assume you have a global solution, and then you just show that couldn't have happened. So that's what we do here, but global now means 2 pi, because whatever these AK of T are, they're 2 pi periodic. So if you want to prove it's global, you only need to go out to 2 pi, or pi in each direction. And so that's another interesting property of this subspace. And so then you can estimate the L2 norm on the double norm. 0 pi cross 0, 2 pi cross 0, 2 pi. It's just the sum of the squares, square root of the sum of the squares of these coefficients alpha k h. And there you can calculate an infinite class of them. I can't calculate them all, but I can calculate them. I can calculate all the ones where h equal k. I can write, there's a formula in the paper. Okay, and then you just throw away the rest and you get a lower bound on the L2 norm. And you find out that if A1 is bigger than 6, that lower bound is infinite. And so the solution couldn't be there.
It's even for analytic data, you can get it. You also get for analytic data, then blow up. Also,
about the nature of blow up?
Yeah.
No, we don't know. This is a big mystery to us. We don't know where it blows up or what that looks like at all. We know it then becomes reasonable again, because after 2 pi, you're back down. We don't have, unfortunately, we do not have any idea of what that blow up looks like.
I meant if the initial data is analytic, you can still produce a blow up.
Yes, all you need, I'll write down here, here's my initial data. U0 of x equals a e to the I x. Can't get much more analytic than that. As soon as a is bigger than 6, the solution blows up in finite time. Okay, so theorem B. Suppose your initial value is now a trigonometric polynomial. So you assume it's again in this subspace, but only a finite. And then now this lambda is now a parameter. In the previous example, I used the theorem about the local existence. Lambda was a factor less than 1. Here it's just a real parameter. So lambda could, but this is a finite series. So whatever the value of lambda, it's a finite, it's just a trigonometric polynomial. So what you can prove is that there's a lambda 0 such that if lambda is bigger than or equal to lambda 0, the solution blows up in finite time, and if lambda is less than lambda 0. Now, theorem A is give you that first part, because you already know that if lambda is large enough, I'm assuming, just for simplicity, I'm assuming that the lowest one is non-zero. We have analogs. In the case where the first non-zero mode is A7 or A8 instead of A1, they're analogs of all this. I'm just tacitly assuming here for simplicity that A1 is not 0. All right, so you know that if that as soon as you get above 6 over A1 of 0, the solution has to blow up in finite time by theorem A. But then you want to show that for all, that there is a lambda 0, which is the boundary line, that it doesn't jump around. It's either above or below. And that you use the radius of convergence. All right, so what else did I want to say here? Okay, yeah, so you use theorem A, and then you study this radius of convergence. And this is the lambda 0 here. So lambda 0 is so as you change the value of lambda, you're changing the radius of convergence at time 0, but then you can prove that that same factor propagates, because multiplying these things by lambda preserves the structure of these AK of t. In other words, if you have a solution of AK of t, then lambda to the AK of t will also be a solution of those same differential equations. So if you multiply the radius of convergence by a factor of lambda in this fashion, that propagates through the solution. So what then you look for is the value such that the minimum of this radius of convergence is 1. So that for lambda bigger than lambda, for lambda less than lambda 0, the radius of convergence will always be bigger than 1, so the solution will be regular, something like that. All right, local ill-posedness. So those are our blow-up results. And now local ill-posedness. So this is a little trickier because, let's see here. Let's put this space on the board. So I'm going to put this here. I'm going to move this over here. This is u of x equals 1 to infinity ak e to the I x. And then I'm going to call, and I apologize for this notation. We couldn't really come up with anything better. How do I call it? Just h plus. And I try to use tildes to indicate that we're in this space. So we're now looking at all functions on the circle whose Fourier series includes a non-zero constant plus the positive terms. Now, we're right away at a disadvantage because we don't have a theorem about well-posedness. In the other case, we already knew the problem was well-posed, so I was using this implicitly. You could say, how do we know that the solution genuinely stays in this subspace? In the first one. Well, the answer to that is that we know the problem is well-posed. So if you have an initial value in this subspace, the first part of the talk, then you know there's a solution that you get by iteration. And each step of the iteration, you stay within the subspace, so the limit will be in that subspace as well. Here, you don't have that. All you have, again, is the formal property, because it still is formally true. If you take a Fourier series of this form, you differentiate it, you don't change, you just bring down k. And if you square it, you don't introduce negative terms. You don't have this simple formula that we had there, because the bk's that you get from squaring now include the same level. So it's no longer a system of linear inhomogeneous equations. It's a system of nonlinear equations. But nonetheless, it's not that hard. And at the level of formal solutions, so here's the formula that translates. This is the standard trick, which doesn't make any sense as a function, but makes perfect sense as a Fourier series, as a formal Fourier series. So you use that same transformation. So here you define u tilde of tx. So here's the thing, u tilde of tx is 1/2 a0 ut x minus a0 t. That has mean value a over 2, a0 over 2. All right, as a function of time and space, that doesn't have any obvious meaning, but as a Fourier development, as a formal Fourier series, it has a perfectly good one, because you just now, you assume that u, so here, so let's see, there's u of tx, you replace x by x minus a0 t, and you have e to the minus, excuse my trembling hand here, it comes with age, I suppose, ak of t e to the minus ik A0 of t, e to the I kx, and as a formal Fourier series, this is perfectly good. And I emphasize a formal Fourier series for each s. And so what the upshot of this is that this transformation is a perfectly good one-to-one transformation between what I've been calling formal solutions. In other words, if you take, let me just go back here. The other thing you can do is you can take something of this nature and plug it into KdV and see what the equations are. And it turns out that the U tilde and it's all consistent. I won't go through all the calculations. You can either start from this, you can either start from this formula right here, or you can just start, you can take this, plug it into the equation, and you can transform the A tilde K equations, even though they're now nonlinear, you can still transform into this one by the same transformation. It all works out, and it's relatively straightforward. So you can solve the formal, this one. So here's the ODE, A tilde of K. There's the corresponding ODE. It's now it's genuinely non-linear because you have the n equals 0 to K. But you can transform it to the other very simply by this transformation. All right, and it's a one-to-one correspondence. Okay, so now what do we do with this? We want to, in some sense, construct or decide whether or not it's locally well posed in L2 if you have an initial value with a non-zero mean. So what you do is you say, suppose you have U tilde, which is the solution of KdV in this space. Suppose you have a solution, you have an initial value with a non-zero mean A0 over 2. You know it's in the space, it's also a formal solution, a genuine solution, it's a formal solution. So you have the Fourier series. Then you can go back and write down the corresponding Fourier series that's in this one by that transformation. The initial value is the same except for the A0. And so you have a local solution here. So you have, if you have an initial value in L2 in the space HS plus, you have the corresponding initial value in H0 by getting rid of the constant term. You have the solution in H0 plus, and you have the supposed theory solution in H or plus, or HS plus or L2 plus. So then that means, let's see here, do I have more on the slide or not? No. Okay, so let me just go back and see if that's why I said it's not as easy to explain. So just say the conclusion again, that if you have a solution in the space L2 plus, it must have come from a solution in L2 0 plus by this transformation. Okay, so what's the first theorem that we can prove? Suppose you have an initial value U0 tilde in L2 plus. That's including the non-zero constant term. And let us suppose that it is not of class C infinity, because you don't want it to be inside the radius of convergence, inside the disk of convergence. So actually, you can say non-analytic, that's good enough. But the important thing is that you do not want it to be, you don't want to have the initial radius of convergence smaller, bigger than 1. Okay, and suppose the mean value is as non-zero imaginary part. That means it's non-zero and it's not real. Then there does not, okay, so that word right there is not. There does not exist a solution, a local solution in both time directions. So here's an initial value in this space, L2 plus, for which there's no local solution in both time directions in L2 plus. All right, sketch of the proof. So by the above analysis, I hope it was somewhat clear, you have to have that U tilde is related to a U in this fashion by this transformation. Now, let's look at rho tilde and rho of t to note the respective radii of convergence of the power series with the A0 and the power series without the A0. They start out the same, actually. Okay, and the point is that let's just jump to the bottom thing, because what you're doing here to calculate the effect of the power series, you want to know see the real part of A0 doesn't change the modulus, doesn't change the radius of conversion of the power series. It's only if A0 has an imaginary part, which cancels the I. And what you can see is that the radius of convergence of the tilde power series is e to the minus I imaginary part of A0t times the radius of convergence of the non-tilde part. So the tilde part is the part which allows a constant term, and the non-tilde part that doesn't allow a constant term. All right, now so that's the first thing. This formula is key, and that's straightforward. But by the hypothesis, what I claim is that the initial radius of convergence has to be 1, exactly 1, which was sort of the borderline case. It can't be bigger than 1, because if the initial radius of convergence were bigger than 1, that would mean that the initial value would be analytic. And the initial radius of convergence can't be less than 1, because you're in L2. Because it's if you're in L2 and then you just have an L2 Fourier series of this type and you replace it by the power series, your radius of convergence is analytic in the entire disk. So your initial radius of convergence of the row of T has to equal 1. And then you have to prove a theorem. I mean, you have to do some work. Everything up to now is straightforward. You actually have to prove, and this is a proposition in our paper, that if the radius of convergence starts out at 1, it stays 1 throughout the entire local resistance. So that's not immediate. I don't even remember offhand how the proof goes. I could find if someone's interested, but that's the non-trivial. Everything else is sort of formally obvious once you start writing it down. The non-trivial part, and in some sense the breakthrough that allowed us to prove this, was observing that if the initial radius of convergence is 1, and in fact, in general, the radius of convergence will not be a constant function of time, but it is if the initial radius of convergence is 1, as long as the solution exists. And that means that for at least positive or negative time, the radius of convergence will be less than 1, and the solution won't be regular. Okay, so that's this. All right, so the rest of it is getting late, and so I think the next, wait a second, here we are. So we have 2 other theorems. Wait a second, I got out of it by mistake. I pressed the wrong button. If someone can help me get back. I pressed the bottom button by mistake. Okay, so that was what I just did. So let's go back to the next one. So let me just state 2 theorems, or explain. I'm not going to even bother stating them. I'll just explain what they are. So so the first thing shows we produced an initial value for which there's no local solution in both time directions. What we show in theorem D is that you can't do a contraction mapping argument around 0. So how does a contraction mapping argument go? It says, given any epsilon and any m, there exists a time such that you have a solution with any initial value, norm less than epsilon exists at least time t, and the norm state is less than m. So what we show is that whatever the choice of epsilon, m, and t are, you can't do it. All right, I won't bother you with those calculations. But what we use in that, well, let me state the next theorem, and it'll be even clearer what we use. So the theorem E, which unfortunately is the one result that we don't have an L2. The calculation only works if S is positive. It's a slightly stronger version of theorem D. It's a result called norm inflation. And there are a number of, I don't remember all the articles that discuss this phenomenon for other equations. You can actually, so what it shows is that you don't have continuity time 0. What you have is a sequence of initial values, which you call phi n, which go to 0, which themselves, you have solutions. So the phi n's go to 0, and at some time interval going to 0, the value of the solution at that time interval goes to infinity. So you can't have continuous dependence at 0. And here, this involves constructing solutions. And that's where we use that Gevrey class, or those solutions, where we use those explicit solutions coming from here, and then we transform them up to this type of solution by that transformation. And then we therefore are able to construct an explicit sequence of solutions that show that 0, you cannot have continuity at 0. Okay, so the last topic, I'll just briefly explain what we do. In fact, I might even sit down for this myself while we're doing this. Okay, so if you take the complex Korteweg-deVries equation and you write it in real imaginary parts, you have system 1, where U and V, so for changing notation, excuse me, we're now calling W instead of U the solution. And instead of X, I'm going to use theta because to insist upon the fact that it's on the circle. And we'll write U equals, W equals U plus IV. So this not complex value solution becomes this real system. So all the results we have talk about this system. There's just statements about this system because there's statements about that equation. So you can ask them, well, suppose you have a slightly more general system. All right, and where P and B started out with P and Q to be homogeneous quadratic polynomials because those are homogeneous quadratic polynomials. And the local existence for these kinds of systems have been studied. And the question is whether some of the results that you've proved for system 1 have extensions to system 2, have analogs. But the method is really dependent on something here. So the question that we were able to answer was, can the same methods apply? In other words, what we needed to do was to translate all of these ideas, boundary values of analytic functions, into what it means here. Or actually what we did the opposite. Roughly what this means, functions of this type are functions real valued, U and V are real valued functions that are Hilbert transforms of each other. And the inside is, as we plugged out, is an analytic function. So we actually study this as analytic functions inside the disk. I'll just, and so inside the disk, W goes to W squared theta, takes analytic functions into analytic functions. So the more general, so we asked, when does this happen? And the basic tool we use is the Cauchy-Riemann equations. And the answer we come to is niet. I mean, it only works for Korteweg-deVries or something here. Where's let's see here. Yeah, so it only works for this system right here, which is essentially Korteweg-deVries. We can explicitly calculate with the Cauchy-Riemann equations right there. You can plug it in with examples, and you see that you can force it that these denominator terms had to have come from Korteweg-deVries or something equivalent. So these methods do not apply to more general systems. And so I thank you very much for your attention and for coming on this last day of the seminar for the semester. Thank you very much.
Are there questions or comments?
So if we take not U squared, but U to the 4th or an even part, we still have preservation of H S0 plus, right?
And even U cubed, I think. Any power. Because as long as you multiply that, so you're not introducing any negative powers, any negative Fourier modes. E to the I k x times e to the I k prime x times e to the I k double prime x is still e to the I k plus k prime plus k double prime x, no matter how many there are. And as long as it's positive, that's still, we try. So the question is, does it work? Actually, I tried to, when we were writing the paper up, I said, well, let's see. And the period, I can't remember, but at some point it became impossible to sort of continue through. In principle, yes. I'm sorry, I anticipated your question. So So let me go back to your question.
So, okay, yes, it works for other powers as well. I was gonna ask at what point, like, what doesn't work?
I don't remember, I apologize. But at one point I asked that question of myself, and I started working it out because if it's going to work for squared and if it's going to work just the other way, and at one point I realized that it was not going to work simply. It might have been the periodicity of the coefficients, but I don't think so. I honestly do not remember what does not work. But it doesn't work just in an easy fashion. And I'm not sure that it doesn't work. You know, it might work, but it requires something else.
Questions or comments?
In the blow-up results, you said that if the initial value of your coefficient A1 is bigger than 6, then there's blow-up. So does that quantity A1 correspond to any of the physical quantities that you mentioned at the beginning? Some combination of mass, charge, or something?
Not that we're aware of. And the other thing too is that if you take the example I wrote up, we can also, so if you take U0 equals AE to the IX, and you start doing numerical simulations. First of all, I don't quite remember exactly how generally do it, but you could also get, the lambda 0, we can get, so we know that if A is bigger than 6, it blows up, and we can get some, I think it's pi squared over something or other, that if A is less than some constant, then it's global. And numerical simulations for this shows that the critical value is not 6. And maybe we can prove that, but certainly numerically, we know that the real cutoff value is not 6. 6 is sharp in that we can produce initial values, which are not this simple, where A0 is just under 6, but the solution is global. So the 6 is probably an artifact of the method rather than anything genuine. Though it's not a complete artifact because it's sharp in at least some sense. But oh, the energies. But you raised another thing. All of these solutions, all those energies are 0. The energies of these solutions are all 0. The integral of u squared of an analytic function, that's 0 by Cauchy's theorem. But also you can, the energies say nothing here in many ways.
The Korteweg-deVries equation was first derived for water waves.
Yes.
And it was derived with real coefficients.
Yes, and you're probably much more.
And what does it mean to have complex coefficients in the context of the water waves where it all came from?
Probably nothing. I'm at least making no claims as to that. But I think that's the reason why people haven't paid attention, because it was just so obvious. Unlike the nonlinear Schrodinger equation, where you right away you have complex valued solutions right from the linear equation right on in. And I don't think people study the. I've seen a few papers on the complex valued nonlinear heat equation, but just considering positive and negative sign. So it is admittedly a mathematical artifact, but again, Jerry and my original motivation. Also, the original paper we wrote was on the 2 soliton solution on the line. Because what we were interested in is that if you write down the 2 soliton solution and you interpret it as a complex value function, you have poles. And the question is, those poles are singularities. And those poles move up and down. And so if you want to know, the grand conclusion of all our work is a conjecture that if you take the generalized Korteweg-deVries equation, which I wrote down for K large, and if you want to understand why blow-up happens, and in fact, at one point, I even started trying to write down an ansatz. The idea would be is that you look at it as a complex value solution in a strip over the real line. In other words, you extend it to be complex value, not only in the fact that, well, it's a real value solution on the line, but then you interpret the real line as Z and it's a complex, okay? And so the idea is you do that more generally, and then you have poles which show up off the real line, they go up and down, and that the blow-up mechanism for K large is when the pole crosses the real axis. And the point is that that's what we see for the two soliton solution, that the poles are moving up and down as time evolves. And so we
wanted to generalize this.
Yes, and actually we have some, we wanted to actually show that that happened here. If we wanted to show that, in fact, the blow-up occurs when the pole crosses the real axis, and what we needed to do was to show that we could not, was that this function rho of t was to continue. We could prove either upper or lower semi-continuity. Had we been able to prove that rho of t, which is the radius of convergence, was a continuous function, we would have had a much better idea of, it would have been much closer to that.
Any other questions or comments? Let's thank Fred again. But you're not going to prove the Riemann hypothesis yet.
No. But the dream is that someone will read the paper and say, oh yes, this is how we had to prove the Riemann hypothesis.
Yeah.